Section 1.4, we're going to take a look at one-sided limits. In a previous section, specifically section 1.1, we took a look at this piecewise defined function, p of x, which was 5x plus 2 for x less than or equal to 7, and x squared minus 4 for x greater than or just greater than 7. And we saw that numerically, the limit of p of x did not exist as x goes to 7, because as x goes to 7 from above, we'd use the x squared minus 4. And that leads to a different place than going to 7 from below, because going from 7 from below, we would have to use the expression 5x plus 2 to evaluate the function. So the function approached different values from the right-hand side and the left-hand side. And if we look at that graphically, there is a big gap in our between the points. So as we went from 7 from below, it looked like we were going to this point. As we went towards 7 from above, it looked like we were going towards that point. So that's what graphically happened. From below, we went to a different place than from above. So the big idea in this section is that we're going to formalize the idea of a limit as x approaches a number from the left or as x approaches a number from the right. The left-hand limit is basically saying we have a function f defined on an interval, and we have L be a real number. The limit of f of x as x approaches c from the left is L is denoted this way. So notice that it's the same notation as our limit notation, except since we want to say x is approaching c from the left, we use a little minus symbol in the exponent of c. All right, so that symbol is always going to be referred to as x approaches c from the left. When I say from the left, I mean from left to right. This is called the left-hand limit. Now, you can do an epsilon delta version of the left-hand limit as well. So to be technical, this limit means that given any epsilon greater than 0, there exists a delta greater than 0, such that for all x between a and c, such that x minus c is less than delta, we have f of x minus L less than epsilon. So we're not going to do a whole lot with the epsilon delta definition of the limit, because we have already looked at epsilon delta definitions. It's basically the same one that we looked at before, except now we restrict x to be underneath c. We can do the same thing with the right-hand limit as well. So the limit of f of x as x approaches c from the right is L, is denoted in the same way. Limit of f of x equals L as x approaches c. But notice that we put in the exponent a plus sign in sort of where the exponent of the c goes. All right, so this is approaching from the right. The other is approaching from the left. So this is called the right-hand limit. So let's take a look at the function that we've established, this piecewise defined function that we've seen back in section 1.1. And we're going to find the limit as x approaches 7 from the left and the limit as x approaches 7 from the right. Now, we can find these limits a number of ways. We can find them numerically, like we did back in section 1.1. And so if I wanted to find the limit as x approaches 7 from the left numerically, what I would do is I would set up a table with x's and then p of x's. And I would make sure that the numbers I plug in were all smaller than 7. So I'd plug in 6.9, 6.99, 6.999, 6.9999. Now, each time you plug that in, because you are underneath 7, you're going to have to use the 5x plus 2. So we take 5 times our 6.9 plus 2. That gives us an output value of 36.5. And then you go 6.99, and then 6.999, and so on and so forth. So what you end up with is 36.95, 36.995, and you get 36.9995. And so you can see that this limit here numerically is going towards 37. Now, another thing we can do is take a look at the graph. We saw the graph earlier. So graphically, what's it mean to approach 7 from the left? Well, it means that I'm going from left to right on this graph. 7 is right here, might be hard to see, but as I get closer and closer and closer to this number 7, I'm approaching this point, which is the point 737. And so you can see in that regard that as my x value approaches 7, my y value approaches 37. Now, it turns out that neither the numerical approach or the graphical approach is the most, neither of those is the quickest way to find this limit. What we can do, if I really want to make this quick, is say, oh, we're dealing with numbers that are below 7. And the evaluation of my p of x, when it's below 7, well, when we're below 7, that's just 5x plus 2. So if I just restrict values to below 7, what I can do is I can say, well, the left-hand limit has to be the same thing as this. And because my p of x is always evaluated as 5x plus 2 when I'm below 7, let's make clear that we're taking the limit of this whole thing. Then I can just use the algebraic techniques I saw in the last section and say, all I need to do is plug in 7. 5 times 7 plus 2 gives me 37. And that's a much, much quicker approach than either the limit than finding the limit using the numerical method or by finding the limit using the graphical method. So let's do that one for the right-hand side limit. So the limit as x approaches 7 from the right, from the positive side of my function, is going to be the same thing as the limit as x approaches 7 from the positive side of x squared minus 4. Because x squared minus 4 is a nice function, nice polynomial, I can simply plug in the number 7 for that. And on the right-hand side, I would get a 45. So finding the left and right-hand limits can be as easy as just saying, well, on the right-hand side, when x is above 7, I use this polynomial. When x is below 7, I use this polynomial, or I use that expression. If it's not a polynomial, you can still use the expression, and then plug that in. Obviously, notice that these limits do not turn out to be the same number, and that's why on the graph, they don't touch. What this example shows us is that when we're evaluating a piecewise limit from one side, we can find those one-sided limits analytically. So we can evaluate a piecewise function limit from one side. We can do so analytically. So here's what I'd like you to do. Here's another piecewise defined function. I want you to find the limit as x approaches 3 from the left and the limit as x approaches 3 from the right for this piecewise defined function. Go ahead and stop the video and do that. On the next video, I'll explain the answers.